So in the first video, we talked about type 1 Pythagorean theorem. In the second video, we talked about type 2, the 30, 60, 90 triangle theorem. And I also briefly showed how you might be able to use the Pythagorean theorem to solve that problem as well, if you needed to. Do it a second way. And now we're going to look at type 3, the 45, 45, 90 triangle theorem in terms of applications. And we're going to do another application problem involving the Earth and satellites orbiting in outer space. So we have satellite A, whoops, let me just do this here so it's easier to focus on the question. Satellite A and B are at the vertices of a right triangle and traveling in the same circular orbit around the Earth. Explain how you know this must be an isosceles right triangle. So let's look at our picture. Here is a circle. Here's the center of our Earth, 45 degrees. 45 degrees is not given to us. Those are things that I wrote in there. We are only given that this is a circle, that A and B are satellites on the circle, and that there is a triangle. And we're trying to figure out how we know that this is an isosceles right triangle. So as a reminder, an isosceles triangle has to have two sides that are the same. And a right triangle has to have a 90-degree angle. In the picture, we're given a 90-degree angle. So that part is given to us. We're given 90 degrees for the triangle. We know that this is isosceles, though, because in a circle, the line segments that go from the center to the edge of the circle are both radii. And the radii, all of the radii of the same circle are going to be congruent to each other. So this distance between the center of the Earth and B and this distance between the center of the Earth and A are going to be equivalent to each other, creating that isosceles right triangle relationship. So the answer to this question, what I put up here, the center of the Earth represents the center of a circle, so the legs are both radii of a circle and therefore equal. And that's the basic idea. Now, what if I had been asked for the angle measures? Like to determine the measure of each of these angles. Well, knowing this information, the next thing that I might say is that the isosceles triangle base angle theorem, so isosceles triangle base angle theorem, states that if two sides are congruent, so two sides are congruent, then the angles opposite those sides are also congruent. So these are the angles opposite those sides. And so that would mean that angle A and angle B are the same as each other. Since it's a right triangle, we've already established that it's a right triangle with the right angle. The only type of triangle that has, only type of right triangle with two angles the same is a 45, 45, 90 triangle. And so those two angles would have to be 45 degrees. And for a little bit more evidence related to this, because I couldn't fit it there, we could say that, like for example, if this was x degrees, because we don't know it, and this is x degrees, because we don't know it, but we know that they are the same, and this is 90 degrees, we know that those have to add to 180 degrees, because that's the triangle sum theorem. Well, if I add x plus x, we get 2x. If I subtract 90, then I get 2x equals 90, and if I divide both sides by 2, I get x is 45. And so it's telling me right there that x has to be 45 degrees. So we could use algebra to explain this as well. The question I have written here is that we just have to describe how we know it's an isosceles right triangle. These are follow-up questions that might be relevant when you're taking the test. Because the next question asks you to figure out some more things for this particular question, and so it's always helpful to get as much information as you can about this stuff. All right, let's look at this question. Satellite A and B are at the vertices of an isosceles right triangle, we've established that, and traveling in the same circular orbit around the Earth. Again, we've already used, so that means like A is going this way, B is going the same direction, so they'll never run into each other. If satellite A is 12,000 kilometers from satellite B, so in other words, we know the length of the hypotenuse. How far are the satellites orbiting above the Earth's surface? So we're trying to figure out how far is B from the Earth and how far is A from the Earth. Since this is an isosceles right triangle, we know that those two lengths should be the same, so if we can find one of them, we'll find the other. And in this case, we're supposed to show two different ways to find the answer. And we want to assume the Earth has a radius of 3,960 miles. So this distance here is in miles, and this distance here is in miles. So we've got a combination of kilometers and miles, which means we'll have to do some unit conversions for that. But we're dealing with a 45, 45, 90 triangle. So let's just take a quick look at a general 45, 45, 90 triangle. If this was 10, rather than this 12,000, how could we figure out the legs that are the same? Well, according to the theorem, this is a root 2, and this is a and a. So whatever the leg is, we're supposed to multiply it by root 2 to get that answer. So if this is supposed to be multiplied by root 2, if this leg is supposed to be multiplied by root 2 to get to here, we should divide by root 2 to get the length of the leg. So what I do is I would set up an equation, 10 equals a root 2, and I would set the model equal to the side that we need. And I would divide by root 2. 10 root 2. Oops, I didn't write that correctly. 10 divided by root 2 equals a. Now, if we were doing this out and trying to get an exact answer, we wouldn't be able to leave it like this. We would then take this and multiply by root 2 over root 2 because we want to get root 2 out of the denominator, and that would give us 10 root 2 over 2 equals the length of the leg, and we could simplify this more because 10 divided by 2 can give us 5 root 2. And this is something that we went over for the previous assessment. So this is the exact answer for A. But we're dealing with an application problem that could use the estimated answer, because when we're going to be dealing with kilometers and miles, anytime we're trying to combine those two units of measure, we're already dealing with an estimate because they don't exactly convert from one to the other. So at this point, I could have figured out what 10 divided by root 2 is. I didn't have to go through all of this work in order to get the answer, but this is good practice. So let's find out what that would be. 10 divided by the square root of 2 is approximately 7.071067, etc., etc., etc. That is about the distance of the length of the leg. Now, if I did these calculations and did all this, and I did 5 times the square root of 2, I would still get A is approximately 7.071067. So these two formats come into play when we are doing our calculations and trying to get the correct format for an exact answer. Either one of these will give us the approximate answer. For our application problem, we only need an approximate answer, so this is what we are using for our application. Now, if we pretend that this is in millimeters, okay, which is very, very, very tiny, then this answer here, I would probably round it to 7.1 millimeters is approximately equal to A, because I don't need a whole bunch of decimal places because this measurement is already so small. Let's go back to our original problem though. So, sorry, that's a little bit blurry. I've solved this problem in 2 different ways. Over here on the left, I've focused on this A root 2, or the 45-45-90 theorem. And the first thing that I did is I converted the radius of the Earth into kilometers, because I decided to do my whole problem in kilometers. And so when I convert that, the radius of the Earth in kilometers becomes 6,371.64 kilometers. And you can see my conversion here. I took the number of miles and multiplied it by 1.609 kilometers per 1 mile, so that miles canceled out and we're left with just kilometers as our units. Now that I have the radius of the Earth, that's just from the center of the Earth to here, I still need to figure out what the rest of this is. Oh, well, that doesn't help me yet because I don't need to do the conversion yet. The first thing that I need to do is to figure out how far it is for the whole thing. I know this length, so with my theorem, I took the 12,000 kilometers and I set it equal to the part of the model that I used, a root 2, divide by root 2. I decided to simplify out all the way, so it looks very similar to what we just did, and we got 6,000 root 2, and then I multiplied that in the calculator to give me this gigantic number with kilometers. So same steps that I just used, but with much larger numbers. And now I have the entire length from the center of the Earth to B, or the center of the Earth to A, is about 8,485 kilometers. Then that's why I converted, is I had to get rid of or subtract or remove the radius of the Earth. And so I subtracted the kilometers to give me approximately 2,113 kilometers is how far satellite B is from the surface of the Earth and how far satellite A is from the surface of the Earth. And again, that answer is in kilometers. I could have also done this answer in miles. If I was doing this answer in miles, then I could take, it looks like the way that I decided to do this last time is I converted the whole length, kilometers, into miles first, and I got a miles, and then I subtracted the number of miles from the center of the Earth, and I got 1,313.63 miles. So either one of those would be approximate answers. Now that's not exactly two different ways to find the answer, that's just two different versions of the answer. Two different ways to find the answer means, well, here I'm using special right triangle relationships, and over here I decided to use the Pythagorean theorem. So I've got a squared, b squared, c squared, or the Pythagorean theorem. And then I substituted in the values that I have. So x is this long leg, x is this long leg. Those are the two things that I don't know. The hypotenuse is what I do know. If I combine like terms, x squared plus x squared becomes 2x squared. If I square this, I get this enormous number. If I divide by 2, I get 72 million. And then I take the square root of that, and it gives me the exact same number of kilometers as before. So totally different way to do it. If I were to try to solve a simpler version of this problem, so let's say this was 10, here's x and x, I can just do x squared plus x squared equals 10 squared, because we're assuming that this is a 45, 45, 90 right triangle. We get 2x squared equals 100. Divide by 2. X squared equals 50. Take the square root of both sides, and x is the square root of 50. When I try to simplify this, I get 5 times 10, which is 5 times 2, which means that we have the square root of 5 times 5 times 2. These are a pair. So again, x equals 5 root 2, which is what we already knew from the work that we did previously, and we already had an estimated answer for that, which we said before was about 7.1. So totally different way to get the answer, but also works. If you recall the way that we found the model in the first place, the way that we solved this theorem and proved it in class, was by using the Pythagorean theorem. So you could have solved the problem using the Pythagorean theorem. And so that's what it's looking for. I hope that that information is clear and helpful.